Good afternoon, ladies and gentlemen, and welcome to this event organised by ASHRAE UK London and South East Chapter. My name is Professor Lubo Jankovic from the University of Hertfordshire, and this year I'm also Chapter President of ASHRAE UK London and South East Chapter. This meeting has the following programme. I will do a short introduction, and then in about 5 to 10 minutes, I will pass the platform on to the colleagues from Integrated Environmental Solutions for presenting the work on creating zero carbon communities, the role of digital twins. And then around 5 o'clock, we will stop for questions and answers, and we will close by 5:30. This is an open meeting with ASHRAE and non-ASHRAE members present. So I need to say something about ASHRAE for those of you who don't know about it. ASHRAE is a 57,000 members strong organization across 132 countries, and it is organized into over 200 chapters, and London and South East chapters is one of them. The acronym historically comes from the name American Society of Heating, Refrigerating and Air Conditioning Engineers, and that name has been replaced by the acronym ASHRAE to reflect the widened scope of work dedicated to advancing environmental design of buildings and promoting a sustainable world. ASHRAE celebrates its 125th anniversary this year. It is run by members, for members, and it welcomes new members. And you can find more about it on these links. Either if you follow the link to ASHRAE main website at ashrae.org, or you can access similar information through ashrae-london.com, which is our chapter website. I would just like to say a few words about forthcoming events. We also have our student branch as part of the London chapter, which is run by colleagues at University College London. And the student branch has organized ASHRAE Distinguished Lecture to be delivered by Karine Leblanc on how to use emotional intelligence to become a better person professionally and personally. That will take place on the 16th of June, and further details will be available through our chapter website. And then on 23rd of June, we have chapter technical webinar on the latest technical standards and guidance to calculate the required filter efficiency to clean ventilation air. And that will be delivered by Peter Diamond of Canfield Limited. And this topic is particularly useful in the context of the current COVID-19 epidemic and concerns, because it will go into the requirements for filtering particle sizes that can contain the virus. You can follow the details of these events, or when these events are going to take place and how to register on the chapter website, ashrae-london.com, and you can contact us on support@ashrae-london.com. So my welcome and intro now out of the way, and now we come to the main part of this evening's program on creating zero carbon communities, the role of digital twins, by Jerome, Ruggiero, and Graham from Integrated Environmental Solutions. And I will now pass the platform on to them.
Thank you very much, Lubo, and welcome to the webinar, everyone. So today's webinar is based on a white paper by Navigant Research by the same name, creating zero carbon communities and the role of digital twins. Basically, we're going to start in with a description of digital twins and the key elements that make up a digital twin. And then have a second part of the webinar where we share 3 case studies with you where the digital twin technology has been deployed in 3 different projects. And as part of this case study presentation, we'll also go into some depth concerning the configuration, the processes, and some of the science behind building one of those digital twins, because some of you people do work on the modelling environment. Okay, so basically, it's a good place to start. It's to define a digital twin. And so there is a lot of different definitions bandied about in the industry. And the definition that we base our technology on is that by the Centre for Digital Built Britain, as you can see there. And what this is basically, it's a combination of technologies. So what we have is emergence of sensor technology, artificial intelligence, machine learning, dynamic simulation. And the digital twin combines these technologies onto a single digital platform. And this digital platform is used from the initial planning stages, master planning, right through the design and right through into the full life cycle operation of the zero carbon community or the decarbonised environment. Now, the physical assets that the digital twins are modelled on contain a large amount of data sets and information from different systems, as you can see in this slide. And so one of the first stages of the digital twin is to take the energy model and dynamic simulations that have been produced during the design and to combine these with the digital asset. And the resulting combination really is the beginning of the digital twin. The Institute of Environmental and Engineering Technology has proposed a maturity spectrum for digital twins to help people understand the different types of digital twin and to help people understand how the digital twins are built up. So there's basically 5 levels. So the first is reality capture, which is basically maps, drone photography and the like. And then a 3D model is constructed. And then the 3D model is populated with static data, which is persistent data, typically from building information models, asset data, etc. Once the static data is populated in the model, then the real-time data is pulled from the physical asset to create the working digital twin. And then the real-time data is then combined, used within the digital twin simulations and calculations, and then 2-way integration is achieved, whereby the digital twin is able to send signals back to the physical asset and start to have an effect on the physical asset. And the last level, and most mature element, is actually autonomous operation. And this is really where the digital twin becomes the all-seeing eye. It's capable of calculations and simulations that typically building management systems and other systems are not capable of because of the information that it can see, because of the digitized physics that is running within the twin. And so ultimately, this results in a much improved environmental performance. And this is one of the keys that keeps these communities zero carbon, or puts basically decarbonisation onto rails effectively to ensure that this process is taking place. Now, when this environment is completed, is what is proposed is basically a shared dynamic model. So what this does is it creates an information platform for quite a large range of data consumers to interact with the digital twin. Let's have a look at a few of these. So your sustainability advisor, or typically energy manager, they'll interact with the digital twin in terms of looking at energy targets, the maximum use of renewables, and other sustainability issues. The actual building occupants, they might be students, workers, residents, they'll interact with the digital twin in a way which promotes energy awareness, promotes behavioural change, and ways which they can contribute and make a contribution towards the environment through their activities. Now, if we consider that the senior real estate portfolio manager, it's important to realise that this technology is not restricted to one particular location. There could be dozens and hundreds of locations in different countries. And so the owner of a large digital asset like a portfolio manager would be looking at comparative data. So comparing the performance of communities or elements of the community with benchmarks, and then looking at those data, so looking at compliance as well in the management of the portfolio. The building services designers, well, they've been involved during the design process, and the digital twin then gives them the capability to interact in a way which is far more meaningful by way of post-occupancy studies and then investigation of any performance gap issues. Now, we all know that performance gap is a big issue in the built environment, and because we're using a single platform, the platform that the project was designed upon can be used to carry out the investigation of any performance related issues. The chap down here in the bottom left, he was simply too happy, or that might have been a moustache. So the urban planners, landscape architects, for example, they'll use the digital twin at the early planning stage to shape the urban environment to get the maximum sustainable performance from the environment. And we'll look at that in a little bit more detail in the coming slides. And then finally, last but not least, is the facilities manager, whose job is to interact with this digital twin in ways to keep this facility up and running, and to manage the different activities that will be going on. There might be renovations, additions, deletions, and the twin is used to simulate all of these things before the actual work takes place. So some of the key elements of a digital twin, they roughly kind of correspond with kind of four main elements. So the first main element is the urban planning element. So as an urban analysis tool, the actual community or development is shaped in such a way as to maximise the use of renewables and to maximise the environmental credentials of the development. So this particular image here is just looking at some solar PV potential on various roofs, and you can see the different colours, intensities corresponding to the amount of PV. And there's lots of other functions that this analysis tool provides. The core of the technology is really the sustainability modelling, the simulation. So this includes the environment, right down to details such as things as trees, the sharing, the solar azimuth, the whole virtual environment is considered in the formation of the digital twin. We mentioned the data consumers, so there's lots of different dashboards and views and interactions, and we'll be having a look at them in some of the case studies shortly. And the other thing to consider is the resource networks within the digital twin. So we're not talking about transmission level, this is sub-transmission, the different resources and the user resources within one of these bounded environments. So I'd just like to spend a little bit of time just on those environments, just to explain this in a little bit more detail in the next slide. So within zero carbon communities, there's generally lots of different elements. So we've got generation, different types of generation, storage, transportation, and different sources as well. So the interaction between the different utilities and the different scenarios that are going to be encountered as these utilities combine can be quite complex, and that's why it's very important to have the correct simulation and the correct design to maximise the performance. It's not just about achieving zero carbon, it's achieving zero carbon in the most efficient way possible. And so, again, the twin has virtual networks that are provided for the resources, and they all form part of the model. So I'm now just going to pass to my colleague, Jerome Messi, who's going to share with you some of the case studies in today's webinar.
Thank you, Graham. Good afternoon. So the first case study I want to show today is a case study located in Singapore. It's an eco-campus at one of the largest universities on Earth. So NTU Singapore used digital twins to deliver a 3D master planning and visualization model, along with virtual testing and building performance optimization for Nanyang Technological University's 250-hectare flagship eco-campus. The goal was to reduce their energy, water, and waste footprints by 35% by 2020, and in the process become the greenest campus in the world. Phase one of the project concentrated on creating a master planning model of the eco-campus, complete with energy signatures of each building on the campus. The model was accurate by 91% for total energy consumption and 97% for chiller consumption. So the master planning model was then used as a baseline to simulate and analyze test bed technologies ranging from improved thermal performance of the building envelope to lighting sensors, chiller improvement, and smart plugs that turn equipment off out of hours. I would like to show a small video to describe more this case study.
With ambitions to become the greenest campus in the world by 2020, Nanyang Technological University have deployed IES's ICL technology across their 250-hectare flagship eco-campus in Singapore. Initially, IES created a master planning model of the entire campus site, accurate to 91% for total energy consumption. That model was then used as a baseline for high-level analysis on a number of energy reduction technology trials.
They had this vision. They wanted to improve the performance of their campus. They said, let's first create a very high-level master planning view on our campus and just tackle the low-hanging fruits. So are we using a set point that maybe is too low? So are we keeping the rooms at 17 degrees rather than more manageable 23, 24 degrees? Very simple intervention that already managed, after 1 year of, let's say, resetting all the parameters, they managed to save around 10%, 15% of the energy. This allowed them to analyze it, to test, to experiment the impact of changes, something that cannot really be easily replicated on site without using the digital twin.
In total, the use of ICL technology revealed a potential reduction in energy consumption of 30%, equating to potential savings of over 4.75 million Singapore dollars.
So the second case study I would like to show today is a case study located in Limerick. So it's how we created a positive energy city. So the project was exploring how to create smart positive energy cities that use digital services to improve quality of life for and together with all their citizens generate more energy than they consume. The Limerick project combines a series of specific actions across the district alongside programs for community and stakeholder engagement. Several initiatives are being explored as ways of creating a positive energy district. Some of them were how to reduce the energy demand of the existing buildings and how to improve the building envelope to reduce energy losses. We also looked at replacing fossil fuels, for example, through installation of heat pumps, solar, and PV. Clearly, Limerick, the project started with a number of clusters, as we call. So we looked at cluster number 1. You can see some green buildings here, and then we looked at specific part of the city, and we tried to reduce the energy consumption and create positive blocks. The first building blocks were composed of 5 buildings, and we created a prosumer, which is an energy efficient building that also gives energy to the block. Some of the prosumer were using very innovative renewables and also became prosumer. So it's a stage approach from one cluster to another. Slowly we're moving into different clusters, and we start to decarbonize the city. Another cluster would be a residential dwelling composed of 21 lower Armstrong Street, and it also became a prosumer. So clearly, digital twin technologies had an important role to play in collecting data from multiple sources, analyzing the impact of proposed programs, and understanding the complex interdependencies between these different elements of the city. It is a stage approach. So digital twin is a tool to create your net zero journey. So you start from the beginning, and you need to create a number of steps. So the first one is how you reach carbon neutrality. So you change the operation, you improve the operation of the buildings, and then you move on to implement low-cost solutions. So for example, that would be becoming a passive building or using renewable generation. And then you become carbon neutral. And then the next step would be to make some deeper renovation improvement and create a prosumer which would be creating positive energy. That's another example where we achieve about 67% total reduction by a number of initiatives indicated here. And overall, we managed to save 1.76 gigawatt hour of total energy consumption for this block. Again, some other area where we managed to improve the building. So a great case study here with specific and bespoke digital twin approach. So the potential impact of a positive energy approach, the benefits clearly are how you produce excess energy, which they can sell outside. The value of their property has increased. You can assume that the tenants would be happy and less time reaction to building issues. And on the other side, for the building occupant, they reduce their utility bills and they have a better indoor environment and more comfortable buildings. The final case study I would like to present today is a case study located in Trent Basin near Nottingham, where we have engaged community in real time. So Trent Basin is a low energy community located within Nottingham waterside, bounded by the River Trent. The development is supported by the Energy Research Accelerator and the Innovate UK funded project called SEED. This is a research project led by the University of Nottingham and A.T. Kearney. It is home to a groundbreaking energy project where energy is being stored on site as well. It was the first storage facility in Europe at the time. The project uses digital twin platforms to integrate real-time data of the energy used, allowing residents to compare household level data with the community average, as well as to see how much energy the project is producing and selling to the grid. The aim of the 3D community interaction model, as you can see on the screen, is to provide a visual tool that promotes public engagement. This is just the project scene, the Trent Basin. And you see a number of windows coming up showing live energy data. They can vary from consumption, the weather, formation for a specific plot here, electricity consumption, and that's the living lab. So this is an interactive screen that you can touch and have data live on screen. Thank you very much. I'm going to pass on to my colleague Jerome, who will carry on with the presentation.
Thank you, Jerome. So I will be providing now some technical details about the case studies that Jerome described. The first case study is about the Nanyang Technological University of Singapore. And as you heard, the project had two phases. In the first phase, we had a high-level master planning. In the second phase, there was a much more detailed building modeling exercise that was done in order to optimize the performance of the cooling system. Now, the second stage required building calibration, and that's on each one of these case studies, I would like to focus on one particular aspect because, of course, we don't have time to go through all the details of the implementation. And for this particular case study, I will be focusing on the process of calibration. I show you all the development that we have been doing, that we had during the last few years. Now, to avoid any hiccups with the videos, as you can imagine, there are several components working together. We decided to record the video. I'm going to start the video now. This case study is about a project with Nanyang Technological University of Singapore. The goal of the university was to create a digital twin for the campus, and the overall vision was to make the campus, the NTU campus, the more sustainable campus in the whole world. The project was in two phases. In the first case, it was maximize the improvements and master plan level. With this phase, they managed to save 10%. This was the master plan that was created for the university. In this case, we are showing the electricity on each single building. As you can see, a shared model, a shared digital twin can be used also to communicate to different stakeholders which building should be, on which building we should be focused our attention. The second part of the project, the project required a much more detailed analysis of the buildings. So very detailed thermal models were built for all these buildings. Also detailed data, minute by minute data from the BMS was imported and was linked to the energy model in order to create a calibrated building. Now, this project was done 3 years ago, so various development has been happening during the last 2-3 years. What I would like to show you a typical process for a very advanced calibration of the buildings. The process of calibration consists in fine-tuning the key parameters of the virtual model so that its behavior mimics much better, in a more realistic way, the behavior of the real building. In this very short video, I'm showing different aspects of the calibration process. The starting point is to use, of course, actual weather data. We should use the data that is corresponding to the year we want to calibrate the building for. The second most important aspect is to use as much input as possible from the real building. For example, if we have the specification of the HVAC systems, if we have specification about the set points at the times of use of the building. And this is actually what I'm showing in the videos here. What I'm using, I'm considering data from the building management system about occupancy. I'm converting this data in profiles that can be used to run the energy simulation. Of course, this will give us a much more realistic results for the simulation of the building. But it still will leave some unknowns because not all the parameters are available in the building management system. So that means that we need a criteria to select the remaining variables. Now, we could either fine-tune the model manually until the calibration criteria is satisfied, or we could use a more systematic approach. And the more systematic approach is the approach that actually I'm showing here in this video. So we choose some of the parameters, for example, the infiltration rate, the various set points, the gains from the buildings, and we perform a sensitivity analysis. Now, what this sensitivity analysis will do, it will identify what are the key parameters that are more important to satisfy the calibration criteria. And we can see here multiple simulation can be run at the same time, on the cloud. And the actual behavior of the total electricity demand, the electricity power, hour by hour, is compared with the calibration criteria. And then once we have identified, for example, the three most important parameters, for example, say the U value, the infiltration, and the boiler efficiency, and with these three parameters, we can then perform a multi-parameter optimization. And with this multi-parameter optimization, we'll identify the actual values of those parameters that will satisfy our calibration criteria. Oh, thank you very much. I hope you found it interesting. And of course, if you need more details, there are many more details in the background. Please feel free to get in touch. Now, the second case study that I would like to show, I would like to give you a bit more detail about the technical implementation, is the Limerick case study. In this case, I would like to focus on the two aspects. The first is the large-scale model creation, and the second is the collaboration between different team members on the same digital twin. Now, once again, to avoid any issues with the presentation, we decided to record a video. So the first case study was the digital twin for the City Exchange project. The City Exchange project was a project developed for the European Union, and the goal of the project was to create positive energy blocks. In this case, we are showing the city of Limerick, and the idea behind the project was that three of these initial blocks of this city would have been improved so that the total energy consumption of the building would have been, first of all, at least zero, or as close as possible to zero, and or the addition of renewable energy would have created a positive net output of energy. So the first thing that we can use this tool. So you can see this is an interactive 3D model. Everything is geolocated somewhere in the world. It can be used as a central repository to share data between different users. First of all, let's have a look where the project is. So we can use this matrix. So we choose PB, and we can choose some particular coloring. Now you can see, let's choose something more interesting. You can see here, the building in red was the first neighborhood that was chosen for this project. There's any metric that is calculated for each building can be applied to this model. In particular, for example, we can show the energy consumption. This energy consumption that was simulated using the ICL. That you simulated using the digital twin. So we can have this representation. And let's invert it to make it more interesting. And we can see here now each energy consumption, simulated energy consumption of each one of this building is shown here. And we can immediately see what are the buildings that are using more energy. Or we can look at something different. For example, we can look at the energy use intensity. And but how do we build this model? So the starting point is the intelligent community design tool. This is the ICD. The ICD is a plugin for SketchUp that allows to build large scale models and analyze them in terms of energy and water and so on. In building each one, this model shows all the different objects all the different buildings that were created. You can see the level of details in terms of the visualization for the whole city is quite high. But building this model by hand would have been practically impossible. It would have taken too much time. So we used data from the Limerick City Council, GIS data from the Limerick City Council that was imported and automatically converted in models. Now, one thing to notice for the IS users in this webinar, that behind each one of this building, there's a full-fledged VE model that can be simulated and analyzed. One thing that I wanted to show one thing that I wanted to show for this webinar was the collaboration. The fact is that the digital twin also allows collaboration between users, because of course we can do analysis that allow us to improve the performance of the building, but the collaboration is a very powerful aspect, especially on projects of this scale. So here, let's have a look at this building. So this building is we can see it in both SketchUp versions. So I've called this Limerick user A, and this second model Limerick user B. Now, in the first, let's assume that the first user wants to make a modification to this building. So we can select the building and we can edit its properties. Now, first of all, when we have imported this model from the GIS file, one thing to notice that not only the geometry was imported, but also all the different attributes, for example, if they're available, of course, building type and specific let's say a specific object ID, condition of the building. So every data point, every attribute that was available in the GIS file has been also associated to the equivalent, to the corresponding model, to the corresponding object in the ICL digital twin. So let's consider this building. So let's suppose that we want to change a properties. Of course, this is I choose the number of stories simply because it will be obvious. So if we change the number of stories, we can see that the number of stories of this building changes. A new AV model, a new IS model will be associated to this building. Now, the only thing that we have to do, we have to synchronize this building with the central repository. And the central repository is the repository that I've shown earlier. So it's a matter of just clicking one single button and log in. So all our project, of course, access to the digital twin is authenticated access. Users can create their own project. They can share projects with other users. So I'm going to add the password and then proceed with the synchronization. The building and now the model has now been synchronized, as you can see from this building highlighted over here. The number of stories for this building is now 10. We can also, the second user though, that is working on the same project, of course, has not synchronized the model yet, so still has an outdated version of the model. But in the same way, because the project has been shared with also user B, the user B can simply synchronize, choose to synchronize the model. User B has to log in, of course, because it's a different user. In this case, I'm using my the same email address. And in the same way as happened before, the user can now download all the data. Now, also, the user B, as you can see from the name of the file, has access at the same data that user A has modified. So this was a very simple example of how the digital twin, the ICL digital twin, can be used, first of all, to deal with large-scale models, but also to collaborate between users. Okay, now as you can imagine, even in this case, there are lots of details behind the scenes, and please feel free to get in touch if you'd like to know more about this project, the digital twin in general. Now we'll be concluding with the last case study about trend basing. Now for this case study, I would like to focus mainly on two different aspects. The first one is using the digital twin for public engagement, and the second one is using the digital twin for community data monitoring. Once again, to avoid any issue, we have decided to record a video. So this is the digital twin for trend basing. Trend basing is a project that we did with the University of Nottingham. And the goal of the researchers and the architects was twofold. First of all, they wanted to engage the people, the residents, the people that live in the community. And second, they wanted to study the behavior of that, try to understand really how people use their apartments. In order to satisfy the first goal, they decided to create this digital twin that's actually shown on a 145 inches touch wall that people can interact with, so they can check properties of the various buildings, of the various properties. And the way to satisfy the second goal was to fill all the apartments, all the homes with several sensors, so that actually the data could be collected and the researchers can actually do the analysis. Now we can see, for example, that each one of this object is, as we've seen in the other case study, this is a 3D interactive model. This is also geolocated, as you can see from the ground map. Now the user can actually touch all these elements of this object and see some properties. Now the reason why you don't see any more properties here is, of course, for privacy reason. But if we look at one specific building, this is the show apartment, then we can see that actually there is additional data that is associated to this building. And this is not only static data, this is also dynamic data. In this particular case, we are showing the temperature in the main living room during the last month. We can just choose the period we want to show the temperature. But not only we can see prop data about the properties, we can actually see also aggregated data. In this case, now we see information at site level now. So we have the solar panel outputs for the last week, we have the current state of the battery, and we also have what percentage of the total electricity for the site was provided by solar panels during the last week. We can also have additional information. We can have the total energy consumption for the site. This data can be also post-processed, so that, for example, we can calculate the average use intensity and compare it with the average in UK. There's also additional information that can be collected, not only data that is coming from building management systems, from smart meters, from Internet of Things. We can also connect it to web services that still produce time-dependent data. In this case, we are showing weather that is coming from a specific web services. With digital twin, is not just about buildings, though. Digital twin is about any device that is present on site. In this case, we have the solar panels. This is the solar farm installed on site. And the solar farm installed on site is supplying electricity via a battery. At the time the project was built, this was actually the largest Tesla battery in Europe. Okay, so this is what the digital twin looks like. As we've seen in the other case studies, this is a model can be shared between users. And the digital twin always has different aspects. It's never only at visual at the 3D representation. But of course, that's the starting point. Now, the starting point, we can see the starting point here. So this is again an ICD model. ICD is a plugin for SketchUp that shows how the building is actually, how the 3D model is actually built. In this case, the data, the geometry was provided by the architect. It was simplified by us, and each of this building was converted in a quite simple way in a semantic model. So behind each one of these models, we have an object, we have some properties, and behind each one of this building, we have a full-fledged energy model that can be used for simulation. We can analyze that, we can check what the properties of these buildings are, and we can see there are a combination of the typical parameters for the buildings, but also a series of custom attributes. Now, this part is important, but also in order to build a digital twin, we want also to connect to the actual data that is coming from the site. This is what the second tool does. This is a time series database that can connect to any source of time series or time series data. For example, building management systems or Internet of Things or any web services that is available. In this case here, we can see that all the sensors in the various apartments and the solar panels, they've been organized by plot name. In particular, there's a feature in the tool that allows to tag some channels, so that makes the organization of the information much simpler. In this case, we can see that we are showing, for example, for 2019 in April, the temperature. One thing that is obvious is that sometimes there are data gaps. This is something that is very difficult to avoid every time we are talking about operational buildings. We can compare not temperature, but also it's interesting because we are building a digital twin. We want to combine simulated building, virtual building with real data. That's why in the same plots, we're actually collecting also data about the simulated building for the same period. For example, here we can show the temperature of this building with the temperature of the corresponding virtual model that at this moment, please notice, has not been calibrated yet. So of course it has some differences. Now, an obvious problem is, of course, to combine now the readings from the BMS data from the Internet of Things with the actual 3D model. The software allows as a feature that allow users to establish some rules that simplify the process of matching time series data, so readings from a specific sensor in a specific location, to a 3D model. Okay, and that's it for me. Once again, I hope you found it interesting. Please get in touch if you'd like to have more information. And now back to Graham.
Thank you very much, Ruggero. I'll just hide this panel here. So just in finishing, we just wanted to share with you the idea that the digital twin that we're talking about here, it is a scalable return on investment. So you can start relatively simply with the maps that you're seeing, the baseline for building energy consumption, and there's different levels of analysis that can be carried out to aid decision making and to provide decision support, right up until the deeper retrofits and investments that we saw in the Limerick case study. So it was just to make that point. And then in summary, we can see our link there to the white paper. You can download this white paper from the website, from the IES website, which is the link to this presentation. It's a very good detailed white paper. And so the summary here is really that the best way to create zero carbon communities is to use the unified platform. I mean, what this effectively does is it puts the decarbonisation or the zero carbon target on rails. I mean, Gerald showed us there the level of detail and the calculations that go into it. And what's happening is that every day, every hour even, there's a constant checking process that's going on to make sure that these developments are performing as they should be, and anything that is going out of kilter or is deviating from that performance, it's very, very easy to highlight that and to go in and to correct it. So any sort of project that you're faced with that needs decarbonisation, you're planning zero carbon, you really, I would strongly advise to consider using a single unified platform for your design and for your entire project. So, and then again, the zero carbon community is digitized physics. It's the science that goes into these models that really provides the benefits. And again, that level of decision support, as we saw in the Nanyang example and on the Limerick example, the investments that are going to be made, that can be made with a very high level of certainty. These simulations that are running achieve between 95 and 99% accuracy. And so what that does is it takes a lot of risk out of the financial investments, and it makes those investments more attractive to get the funding for the projects as well. So I'd just like to leave you with that and consider these things as you go forward. I think we've now got we're finished on time, and we've got plenty of times to take on some questions. So.
Well, there's a question from Brian, says define net zero. Well, I mean, the definition of net zero is the total net carbon produced in 1 year. Of course, it doesn't mean that building doesn't produce any carbon, but it means that overall in 1 year, there is a compensation between the carbon that is emitted by the building and the carbon that is avoided via renewables, or in a particular case, for this particular project, they were also interested in looking at potential sequestration, for example, from trees. And that's something that I couldn't go into much details, but every model that you have seen before can be actually simulated across multiple years. So potentially we could be running a thermal simulation for 2020 until 2050. And we also could include the impact of carbon sequestration from trees. So I hopefully answer your question. Yes, okay, for EcoCampus, 91% accuracy was achieved. How was this achieved and how could be improved? Wow, I think as a, let's say, building physicist, 91% accuracy to me already is shocking. So I consider just an incredible level of accuracy. But the only way that we have to reach the level of accuracy is using building calibration, the process that I've shown in the first case study. So that means that we start to have a geometry that resembles quite well the geometry of the building, and then we start to fine-tune several parameters, including, for example, the air conditioning system, the level of infiltration, the property of the envelope. And what you have seen in those charts that I've shown before, that sometimes we manage to have the level of accuracy not in the monthly calibration process, but actually in the hourly results. So that means that the building is behavior. Of course, as Graham said before, Calibration is not a one-off process. Calibration is something that needs to be refreshed continuously, because as we know, buildings are not very predictable, so we need to continuously adapt the digital twin. Now, I see there are lots of questions that are coming. So define net zero, we've answered this for EcoCampus. So this project is only applied to UK or can be extended for other countries in Europe. It can be actually extended to every country in the world. So if you're talking about the positive energy block, actually the overall project is for 7 cities in Europe that are called the lighthouse cities. But then the idea is to share it, to replicate the principle across the whole continent. But in terms of the actual approach, we also have an experience with a project in the Middle East, specifically in Dubai. Actually, we've signed a contract with them. They would like to use the same logic of starting from minimizing the energy consumption from the building, known as a B-lean. That's not what usually we say in UK, and then trying to make the block positive using renewables energy to becoming green. Okay, this project is only a place where we responded this. So have you considered lifetime energy output versus energy required to create? At the moment, we are not considering embedded carbon. But it's definitely a good point. The fact is, as you know, like in this case, it's not the more you reduce the building actual energy consumption, the more reduce the operational carbon emission, the more the embedded carbon becomes important. But it's definitely something that we would like to take into account in the near future. What else we got? What level of details digital twin models incorporate with HVAC system in different buildings that is using Apache Sys or Apache HVAC? That's a very good question. And every time that we are talking about the digital twin, the level of accuracy is really strongly dependent on the use case. Creating an extremely accurate digital twin for no reason, it really is something that we try to avoid. The system, the process that you have seen, the case studies that you have seen now, the Trent Basin is using Apache Sys at the moment. Also, it's in UK, so there are no major issues with humidity. The calibration of the NTU project was using the full Apache HVAC because it's Singapore, so of course the impact of humidity is much more important, and I hope so. It really we decide every time we need to build a digital twin. So here, there's another question: hi, where are the location of the sensors? How do they deal with the difference of different measurement results of sensors of different brand? It's not really something that we consider. Of course, there's every model. Let's say every model is wrong. There was a famous quote: "Every model is wrong. Some models are useful." We try to focus on useful model. The difference in measuring of 1/2 degree of temperature is not something that we believe is relevant if it is compared to the scale of the problem that we are trying to solve. But it's definitely, of course, ideally, we tend to partner with either control specialists or building specialists in general, of installer. Hopefully, you know, we tend to let's say believe that proper sensors have been installed. One thing that, let's say, is kind of related to this. Bear in mind that behind each one of this model, there's a physics-based simulation. So that means that what our digital twin allows us to implement is also the concept of virtual sensor. And this is only possible because we are not using only recording of a real sensor on site, but we actually relying on calibrated model. So this can produce additional information that normally wouldn't be available in a building management system, for example. And is there a source from which you can determine how to calibrate and what to tweak? Is it based on your experience in modeling? This is a very, very good question. One thing that maybe I hope I probably didn't come across from my demonstration, that the reason why we are using we are first using the weather data. Then we add to the building every data that we know. So that means, for example, the schedule of the HVAC system. That's something is known. But then there's also the other aspect. Okay, now we need to understand all the variables that are unknown. For this reason, we want to approach the calibration process in a systematic way. That's why we perform a sensitivity analysis first. So it's not based on experience. Of course, the experience of the engineers is always important, but the fact is we try to abstract, we try to make the process as systematic as possible. So the first step after inputting all the data that we know is to perform a sensitivity analysis to identify what are those unknown parameters that we still don't know. Once we identified, for example, the top 3 parameters, the top 5 parameters, then we perform a multi-parameter optimization so that actually we minimize the errors in the either, for example, the total energy consumption or the monthly energy consumption. To minimize, when I'm talking about error, what we use is the ASHRAE calibration criteria for both hourly calibrated building or annually calibrated buildings. So hopefully this answer the question. So the effect on gross now versus net zero. This is the same about the third question. Let go someone else. So within the case study discussed, was the available sensitivity devices you mentioned sufficient for either calibration, and was there a requirement for retrofitting buildings? This is a very good question. I don't want to answer like all the consultants. Really, it depends, because there are some projects, for example, a calibration we are working on now, where the number of sensor is, for example, the trend basin. The trend basin, there are, I think, something like 20, 30 sensors for each apartment. So the level of detail in that project was extreme. For another project we are working now, sometimes we have to work with what we have available. But one technology that we are exploring at the moment is the LoRaWAN sensors. The problem with adding the sensors is not just buying the sensors. In fact, is that if we got a building, for example, that need additional sensors in the corridor in some spaces, or buildings for which we are measuring only temperature, but we want to measure humidity, carbon dioxide, and so on. The problems in this case is that, of course, we cannot wire all the sensors. At buildings that are not super new, of course, all the sensors will be wired. But what we're doing now, we're working on a project right now. We are investing quite a bit in the LoRaWAN sensors. Now, LoRaWAN is a radio technology, so there is a wireless technology based on the protocol. It's called the LoRaWAN, that allows these sensors to work for up to 2 to 10 years. They use a different network, but the fact is they can literally be plugged on the wall and they just start to work. So in terms, at least when we are talking about sensing a variable, so sensing a temperature, sensing an airflow or carbon dioxide, this is an alternative solution that can enrich the data set that we use for the calibration of the project. Okay, when the case is discussed with the available sensors, I hope Xander answered your question. So what would be a reason to create an extremely accurate digital twin? Absolutely, this is the point that I was trying to do before. In general, there's in most cases there's really no reason to create a digital twin that is incredibly accurate. As we know, there are always so many unknowns in a building. Usually the error, let's say, when we simulate a building, the error that we make, because there is something that we just don't know, we cannot know if maybe a meeting room will be occupied tomorrow. Usually those errors are much higher than the error that we make in the search of, I would say, it's almost an not required extreme accuracy. And so far, at least I've been working in this industry for almost 20 years, in this digital twin for 3-4 years. Honestly, I've never found a case for which we really needed to do a model that was extremely accurate. Of course, if that didn't require time, resources, and sensors, we all like to do it, but sometimes it's just not practical.
Thank you, Ruggero. I just wanted to add as well that we can create a digital twin from OpenStreetMap without any data, and then the digital twin will estimate the heating and cooling demand easily, and then we can go more and more into a more detailed model.
Okay, thank you, Jerome. So for modeling, do you have plans to develop plugins for BIM software such Revit? To answer your question exactly, yes, we have plans for that. At the moment, we we can import the digital twin, we can import BIM and Revit in the virtual environment. As if you know our software, probably you know. As you know, every time you deal with geometry, it's always more complicated than it looks, but the answer is definitely yes. At the moment, when we are looking at master planning level, or when we're looking at portfolio level, the accuracy that a BIM provides, or the level of details that BIM provides, is not required. But as you have seen in my first case study for NTU, the level of detail there was extreme. And of course, if a BIM model, a full BIM model, had been available, maybe would have simplified the process of creating the geometry. And the second, so if you're not including embedded energy, again, Brian really cares about embedded energy. Maybe I'll try to answer that question, and then I'll respond.
Can I maybe, Rogero, maybe
please.
I can help you out
Yeah,
here.
please.
From my experience of a range of different simulation tools, I found some that actually have embodied carbon emissions as part of their construction database, and you have construction database in your
Yes,
tools. So it could be a simple extension of adding embodied carbon to your construction database, and letting the tool do the calculations. So I don't think this is a big problem, except, you see, in the tools that I have been using, embodied carbon emissions can only be positive. They cannot be negative. Now, this is a problem because there are some materials like hemp lime biocomposite, which comes with a significant negative embodied carbon. So what I can suggest to you as a team, when you are looking into this, is when it comes to including carbon emissions into your construction database, that you allow the user to specify negative carbon emissions, because there are materials coming on the market, or have been on the market already, that have negative carbon emissions, but they're not taken into account by existing tools.
That's a very good point. Also, I mean, we should also consider that, let's say, the majority of the building already exists. So that let's say the carbon has already been emitted, and of course, embodied energy, I think we're talking about mainly new buildings. The fact is, what lots of the work that we're doing now is also for existing buildings, for which, let's say, it's too late. But I definitely take that comment into account. I will report to my colleagues because it's part of the virtual environment, the simulation part. So once you have identified an area for improvement, you simply provide the client with information and provide a solution. Also, you have shown case study within the UK. Are you only applying ASHRAE standard, or do you align with CIBSE? We definitely align with CIBSE as well. And we usually tend to, we can analyze the case, we can propose a solution. What is happening in the, let's say, in the long term, that we would like to almost deploy a digital twin for the client. What would, let's say, in our long-term vision, the digital twin, the digital model becomes a digital asset that the clients can use themselves to improve their own building. Of course, at the moment, it requires intervention from us. We need to build a digital twin, but once we identify energy efficiency measures, for example, we definitely work to the client for the implementation, but most importantly, also for the measure and verification, because everything in theory works, but the fact is what we try to do is to measure and verify that actually the predicted energy savings actually are actually obtained. And not only we use standard from ASHRAE, we use standard from CIBSE, but there's a recent project, when I say recent, maybe 4 or 5 years ago, that actually required us to generate completely new usage profiles for different building typologies. So if you, let's say, if you have access to one of this ICL tool, you will see that there are alternative user profile, load profile, lighting profile based on this European research project that was done a few years ago. So hope Kylie ever answered your question. And we've got Josh here. So how do these neighborhoods relate to the surrounding area? For example, is there a business district where people drive to take public transportation, or do most people live, work within the zone of analysis? It would be interesting to understand more about the occupants function of that. This is a very good question, because again, I cannot go into much detail, but what the project tries to do, it not only looks at the energy of the carbon for the specific neighborhood. There's actually a part of the project that talks about socioeconomic indicators. Socioeconomic indicator, practically saying, okay, how often people use the car in this neighborhood. So one example that says, for example, is how the installation of electric vehicle charging station is going to change the access to this point, how the location of the grocery store, of the pharmacy. Of course, all this was pre-COVID. All this analysis was pre-COVID. So how this impact the use of the building? And that's why they're trying to do what the project is trying to do is a holistic, let's say, let's call it net zero building, because not only we want to save energy, but for example, one of the goals of the European Union is also to reduce the fuel poverty. So there's a partner in this project, and not only they uses the data that we calculate. So we simulate the building, we calibrate the building, so we can understand how much energy the building is producing in a year. But then if we propose a solution to improve the performance of the building, means that the building will require less energy. So as a consequence, will reduce fuel poverty. So as also a social impact. And but you have absolutely a good point. It's not just, let's say, it's not just about energy. Let's see other questions. So is there any workflow in place we would utilize BIM models from the design phase? Yes, because BIM models can be imported in the V. And so those models then can be used to start, let's say, to begin the construction of the digital twin. But I mean, if you ask the question, probably you have probably dealt with the BIM model. You know that it's not always so easy to import a BIM model from and import it into an energy model or any other simulation for the matter. Luber, just see they've got so are you looking into machine learning so that you spend less time calibrating? Absolutely yes, absolutely yes. And the fact is, if you notice, and during my presentation at some point, I talk about the inevitable case of missing data. So we are trying to, let's say, we don't want to use machine learning for the sake of it. So for example, what we are doing, we actually develop a tool that automatically fills missing data in the data that is coming from the BMS. And an energy model, in order to do the calibration, needs a data set that is relatively clean. So previously, we had to do the process. We have to do the process almost manually. What we do now, we can actually choose. We can actually replace. We can fill the gaps. Of course, if these gaps are not of months, although even in that case, we can replicate it. What the system does, analyzes the pattern for weeks or months before, takes also into account the external weather data. So it builds a model. It uses the models to fill the gap. Now, will the data, let's say, filled gaps, the new value, be the real one? Of course, we all know with those data, the data is lost. But because we use a combination of the physics-based model and machine learning, it's probably the best estimate that we can do. That also other approach that we are using, not at building level, where we use reduced order models, where actually we can read the data, and so we can build a very basic, a very, let's say, rough model of a system based only on reading the data. So we are using machine learning in several aspects. We're also using machine learning to predict anomalies, because when the building is connected, there's another project that we're not shown today, but when the building is connected to the building management system, what our system does in this other project is continuously looking at the data. It builds a model of behavior of this building. So that means that it continuously analyze the data. And when, for example, the reading of the flow temperature of the boiler goes outside the range for a certain amount of time, so outside the expected range for the particular system, then it raises an alarm to maybe to the facility manager, to the estate manager, to show that there's an anomaly in the system that could be a source of concern. So if they already exist, maybe keep them. Try to check. Okay, so this is again Brian, and well, no, it's not that we don't want to do it, because of course you can imagine we have got several projects, several customers. It's also always a matter of priorities, let's say, but we'll definitely take that into account. and operational resilience into account, we have a life cycle model in the visual environment, taking into account the fact is that the equipment stops working in a proper way after a while. But as you can imagine, it really every time it depends on the kind of equipment. Lighting doesn't behave the same way like a filter for HVAC system or a fan behaves. So I don't see other questions.
I think that's the end of the questions. We can just leave it to Lubo for any parting comments and
actually,
say thank you to everyone.
Actually, yeah, thank you for this. Thanks for the audience and for the presenters. I wanted to ask the question via the questions box, but I can only answer questions. I can't send them. So I just wanted to ask: does your tool calculate only what is inside of the buildings, or does it do any external environment? Does it do heat island effects and things like that?
We have some tools to calculate an approximate Italian effect, but this tool that you're looking now is for internal buildings. One thing that we have not touched today is the connection between buildings. Was the last slide that Graham presented. So like the overall resources, but for example, it's not looking at outdoor comfort. It's not looking at the impact of trees on ventilation. We offer that as a service, but it's not part of this suite. This ecosystem. I call this an ecosystem of tools, because when we're talking about this digital twin, is not one piece of software. It's a collection. It's an ecosystem of things. Because
I think there's another question. So,
yeah. Sorry. Let me reopen my panel again. Okay. Okay. Thank you very much. The presentation. Would it be possible to share energy between assets in the platform? For example, energy positive building exporting energy to neighbor buildings using energy smart central PV storage system. Absolutely yes. That's actually one thing that we're working on now. Not only we can exchange energy, we can exchange resources, because there's one tool that we have not shown today that is called the virtual network. The virtual network allows you to create a network of building, because every building in the city doesn't live by its own, and so that can actually shows the connection between different buildings. For example, the typical example is the electrical transformer that is serving 10 buildings, but also when we have a district heating network. So the same electricity network is actually providing electricity for the pumps that is moving the water around the district heating network. Of course, once we add installations such solar panels, PV panels, or wind turbine, or heat pumps, that means that actually we have to analyze the system as a whole. We cannot analyze one building at a time. We have to run the simulation of the building, but taking into account that, for example, the energy that is producing from some solar panel can be fed to different buildings at different time of the days. Or, of course, this becomes much more complicated. These tools becomes very useful when we add storage to it, because of course everything with storage can be delayed. And but it definitely, yes, we have not discussed that today, but it's definitely possible. Please feel free in touch, because there's also a very interesting part of the digital twin within the context of the community, rather than just one single building.
So thank you very much. Cheers then. Thanks.
Bye-bye.
Bye-bye. Thank you.